Aloha. Welcome to Live from NOIRLab at Hawaii. My name is Jamika Marshall, and I am an outreach assistant at the International Gemini Observatory, which is a program of NSF's NOIRLab. Joining me today as moderator is my colleague, Leilani Losi. So please post your comments and questions in the YouTube chat anytime, and Leilani will come back on screen throughout the presentation to share your questions and comments with today's guests. So if it's your first time joining us, welcome, welcome. We'll do a brief background or review about Gemini Observatory. Today, so the International Gemini Observatory is one of 5 programs of NSF's NOIRLab, which is the preeminent U.S. National Center for ground-based nighttime optical and infrared astronomy. Gemini Observatory is composed of twin telescopes, Gemini North, located on Mauna Kea at an altitude of just under 14,000 feet, and Gemini South, located on north central Chile's Cerro Pachon. Gemini's telescopes observe invisible and infrared light. Its 8-meter reflectors collect this light with mirrors that are coated with a special layer of protected silver instead of aluminum, which is the more traditional coating for large telescopes. Now, Gemini's mirrors are made up of ultra low expansion glass and is about 20 centimeters thick. Now, as you can see, Gemini has very large vents, which are opened at night, which allow the cold air to flow through the observatory, producing very stable images. The advantage of having observatories, telescopes in both hemispheres is that Gemini Observatory can observe objects throughout the entire night sky. So a bit of a science update, and one of our latest press releases is on Jupiter. By Jove, Jupiter shows us its stripes and colors. So detailed new images of Jupiter captured in different colors of light reveal a multitude of atmospheric features. These 3 new images reveal exquisite details in its atmosphere. They provide rare infrared, visible, and ultraviolet views from the Gemini telescope and the Hubble Space Telescope. The portraits feature weather phenomena such as the Great Red Spot, superstorms, and giant cyclones. Comparisons like these highlight the power of different kinds of light to reveal details that would otherwise remain hidden. Now, the scientific story behind these amazing, striking images is actually told in a full new NOIRLab Stories blog post. So as well as discovering the science behind these images, we invite you to actually inspect observations of Jupiter at home. There are 3 interactive images that let you compare observations of Jupiter in those 3 different light waves that we were just seeing in the video. It allows you to peer beneath the gas giant's clouds. So in the video description, we'll have the link to the CosmoView 28 that we just saw, as well as a link to the NOIRLab Stories blog post and the related press release on, it'll be in that video description. So please do check that out. And don't forget that if you love amazing images, we do have images that you can download, not only of these 3 different views of Jupiter, but of all of our images. So check out the NOIRLab image gallery. Okay. Oops, sorry. So now for today's guest. Aha. So Vinicius Placco is our guest today. So those of you who have joined us in December may remember Vinny. So I'd like to welcome Vinny. He is an associate scientist at NOIRLab CSDC, and that is the Community Science and Data Center. He's working in the U.S. National Gemini office since September of 2020. Now, Vinny obtained his PhD in astronomy at the University of Sao Paulo in Brazil. He held postdoctoral positions in Brazil at NOAO in Tucson and as a Gemini Science Fellow in Hawaii. Between 2015 and 2020, he was a research assistant professor of physics at the University of Notre Dame. His research is in the field of stellar archaeology, which focuses on the origins and evolution of the chemical elements in the Milky Way galaxy and the universe. Welcome, Vinny.
Hello, everybody. Thank you very much for having me again. Really excited about this presentation. So let's see, I can start my screen share and we will move forward.
Perfect. Okay, so the title is a chemically peculiar star found from this color. So can we start, first of all, with you explaining to us, Vinny, for astronomers, what is a metal, just to get us started?
Sure. So as Jamika said, so this is a presentation about a recently published paper about a peculiar star we discovered in the Milky Way. And that star is peculiar because of its chemistry. So there's some weird things that happen on the atmosphere of that star, and we'll talk about that in a moment. So when talking about chemistry, Leilani, you have something, or you have a question already?
It's not a question, but we do have a shout out from the chat, I believe from your brother, Mauricio. Said, have a great talk, and he's proud of you.
Yeah, he's one of my brothers from the heart. Yeah, so thank you. Yeah, so well, I'm glad to see people enjoying this. So we're talking about this chemically peculiar star, and to talk about that, first we have to talk about some chemistry, right? And I know that people don't like too much chemistry in high school. I was one of those as well. I'm not a chemist, but we need to talk a little bit, just show the periodic table, as you may know from high school, right? So in here, we have all of these different chemical elements, and we know they have all sorts of different origins, right? You can talk about the lanthanides, actinides, and you can see all the different classes here, noble gases. But for astronomers, at least at first, we have a slightly simpler classification of elements, because we try to tie the elements into their astrophysical origin, right? So trying to explain where all of those elements come from in some sort of an astrophysical context, not a chemistry context. So for astronomers, everything that we had in the universe when the universe began after the Big Bang was, okay, so this was only hydrogen and helium. So these were the only two things we had on the entire universe. So for the astronomers, everything that is not hydrogen and helium, it's a metal, right? Then we can talk about specific different classifications. And as you see here, this is a slightly different periodic table than the one you saw. So astronomers try to classify elements by the place where they are mostly formed. So you can see here on the captions, you see dying low mass stars, merging neutron stars, exploding massive stars. So these are the astrophysical sites where astronomers believe those elements came from. So from an astronomical perspective, everything that is not hydrogen and helium, we consider a metal, right? So then we are going to talk about this interesting ultra metal poor stars, and that means that they have lots of hydrogen, lots of helium, and not a lot of, well, everything else. And one of the questions that this research and my research in general tries to answer is, so how do we go from this, right, only hydrogen and helium at the Big Bang, so we know that that happened, how do we go from this all the way to this? When we look at the sun today, when we look at our own bodies and things here on Earth, we can find most of these elements that you see on the table. So how do these elements form? So we know today that all of those elements are formed inside stars, most of them, either in burning stages inside the star when stars are evolving, or explosive stages, when you see, for example, supernova explosions or neutron stars. And so all of those different types of explosions. And when stars are evolving from, as you see here on this very nice picture, stars going from supergiants to red giants, then exploding as supernova, all of the chemical elements are formed in one stage of the evolution of one of those stars. And we know that that's a fact, right? So then once those stars form those elements, maybe inside of their own cores when they are evolving or when they explode, once that explosion happens, all of that material is just thrown off into the interstellar medium. So then you have a polluted gas cloud with all of those different elements. And those different elements, they will serve as the seed for the next generation of stars, right? So this, for example, if you have one star, that star evolves, forms lots of chemicals, explodes, enriches the medium with lots of chemicals, then the next star is formed out of that pre-enriched gas, and then it retains that chemical fingerprint. So when you look at the atmosphere of the second star, you can actually tell what happened with the first one. So you do some sort of forensics in a sense in here. And in particular, this field of stellar archaeology that I work on, I think we're really interested in knowing how the first stars to be born in the universe, how they were in terms of their evolution, in terms of their masses. And one way of doing that is, so if you look at this graphic here, we are assuming that at the Big Bang, we only had hydrogen and helium. So the stars that were formed only out of those hydrogen and helium, they were supermassive. They had 10 times the mass of our sun or 100 times the mass of the sun. And because of that, because they were so massive, they evolved super, super fast. So a couple million years, they evolved, and then they exploded as supernova. And as you can see here, they just dumped on the interstellar medium all of those elements: iron, oxygen, nitrogen, carbon, and many more. And those elements, they serve as the seeds for the second generation stars. So what we think we can find today and observe, and the star that we're going to talk about today is proof of that, is that we can actually observe today, 13 billion years later, we can observe the surviving second generation stars. And we, call those ultra metal poor stars. Jamika, you have something? Yeah.
Yes. Okay, so the second generation of stars are ultra metal poor stars. So how do you go about finding these ultra metal star pores? And reading your paper, of course, I see that you use some photometry and spectroscopy. Can you give us a little bit of insight for those of us who aren't quite familiar with photometry and spectroscopy? What are those, and how did that help you find these stars?
Okay, great. So there's two main techniques that we used on this particular research. And one of them is called photometry, and the other one's called spectroscopy. So I'll just have a couple of brief slides about those. And so the first one is photometry. And photometry, as the name says, I think there's a definition there, it's just measuring light, right? And you can think of photometry as maybe taking pictures of the sky or taking pictures of something with the camera on your phone. Jamika, do you have something?
Oh, no, sorry. Nope, I'm good. Continue,
okay,
please.
Sure. Okay, sounds good. So it's the same thing as taking pictures with your phone, right? But then astronomers, we want to do a little bit better than that, and we want to quantify the brightness of all of the objects that we see on a given part of the sky, right? So if you take an image like this one you see here, for example, this is a galaxy. I forgot the exact name of the galaxy, but when you look at this, you can see that there's lots and lots of points sprinkled all around the picture, right? So what astronomers want to do is they want to develop a technique to identify each and every one of the bright dots in here and actually measure, quantify how bright they are. Okay, so then there's some automated techniques. People can do this by hand depending on what they want to do. So the result of this, it's something like this. So each and every one of those squares and circles is a source identified by an automated algorithm. And what that algorithm does is say, hey, for this particular square, I can measure a brightness and I can give a value to that brightness, right? And this is important for astronomers because if we can measure those brightness and colors, we can do all sorts of different analysis and determine lots and lots of different parameters for stars. So one example, and we use this technique to find one of our stars. So that star is somewhere in here. It's one of those squares. So we need to be, well, clever enough to know how to identify the interesting ones amongst all of those. So what astronomers do is you see the pretty pictures on the news, and these are the ones that we use just for show. But what we are really interested in, sometimes we look at the structure of those things as well, but we are really interested in transforming those images into something like the thing you see on the right-hand side. So this is a graph that is just the surface temperature, the intrinsic luminosity, and there's so much more you can do. But this is just a small taste of what photometry can do for you, right? So again, photometry is just taking pictures of the sky and try to translate that information into numbers that you can actually work with. Spectroscopy is a little bit different, right? Spectroscopy is a little bit a more powerful method. And the way I like to see spectroscopy is just, well, splitting light into its constituent wavelengths. So what you're doing, and you're just getting the same light coming from the sky, but then you're some sort of shining that light through some sort of an interesting instrument that will give you something else. And the main correlation that I can make this is just rainbows, right? The reason we have rainbows, and you can see here on the left-hand side on the bottom, is you have light coming from, for example, the sun when you see a rainbow. That light gets inside water droplets, it gets reflected, refracted, and that's how you see a rainbow getting formed. So we use the exact same principle to do spectroscopy with stars. So we point to a given star and get that light from the star shining through some sort of a prism or a dispersing element, that's what we like to call. And once we do that, we see something like the picture on your right. We see the rainbow, we see all the different colors, but we see all of those weird discontinuities that you can see here. And each and every one of those tiny lines, it's an indication of the chemical composition of a given star. Right? I won't go into much further detail on this, but I just wanted you to have a sense of how we get, for example, the chemistry information from stellar sources, right? So you just point to a given star, let the light shine through a prism or a dispersing element, and then you record that information, and then it gives you something like this, right? And then each and every one of those lines here gives you an idea of each element that it's on the atmosphere of that star. So I don't look at rainbows all day, so they're slightly less maybe romantic than that. So this is how they look on a formal basis. And I won't go into detail on this as well. I just wanted you to have a look at the top panels here. They are showing the light from 4 different stars, in this case, just getting dispersed by a prism type thing. Right? And then you see all the discontinuities here. So what we do is we transform that information, this image here, into a graph like this on the bottom part of each panel. And then by measuring those dips here and correlating those dips within a specific number here, we can actually tell which elements are in the atmosphere of the star. So in this particular case, there's a lot of hydrogen, then you have calcium, carbon, magnesium, and you can play this game with pretty much all the elements, not all, but most of the elements on the periodic table. You can actually do that, right? So then for this particular discovery, we used both methods. We used spectroscopy, and we used also photometry. Yeah. Leinani, you have something?
Hey, Vinny, we have a couple comments on the YouTube chat. One is in Spanish, so I don't know how to say it, and I don't want to mess it up, but I've put it in our Zoom chat box here for you. And then our second comment is, thanks for the great explanation of photometry and spectroscopy.
Oh, thank you. Okay, so I don't think I see the comment here on the chat.
I see that comment, and that appears to be French.
Okay.
So I'll have to translate that and come back.
Okay, so we will, yeah. So we'll address for sure. Yeah.
Thank you, Leilani. I have a question, Vinny.
Okay. Okay.
So let's see, it was slide, I think this was slide 11, the slide with all the squares and the dots.
Oh, that's okay. So let me just go back to that if I can. Oh, nope. Here. All right.
Yes, this one, yes. You said this was an automated algorithm. Do you have your software engineers on your team that writes this algorithm for you?
Oh, we do have people within NOIRLab that do that. And we do have, well, since people have been doing this for, well, decades now, we do have a specialized software. They're just available for free online that you can use. Yeah, no, exactly. And this particular one, there are many services online now that anybody can go there, get a picture of this, and just see which sources are identified. Yeah, so it's...
Oh, wow. Okay. We'll try to get that information from you later and put that in the description box for anyone who's interested in exploring some of these squares and dots to see what's actually there.
Absolutely. Yeah. Yeah. Oh, okay. I see the comment now. Oh, so it's actually in Portuguese.
Ah, it's Portuguese.
Yeah. It says, well, good night. Congratulations. Yeah. Well, it's congratulations before the presentation ends. Well, it's dangerous, right? We're not there yet, but I'll take it. Yeah. Okay.
Yeah.
That comment was from Silvio Placco.
Oh, okay. That's my dad. So, hey, that's suspicious. Yeah. Okay.
Fantastic. Well, we're so glad to have your dad in the chat with us today. Okay. And so another question, if I can, just loving all of your charts and graphs here. They really explain the data pretty well, especially for me, someone who needs to have numbers visualized. So we're getting into the photometry, narrow band photometry versus your medium and high resolution spectroscopy. And I definitely noticed that you had those distinguished, differentiated in your paper. Can you talk to us a little bit about that?
Sure. Yeah. So then we use those two techniques, photometry, spectroscopy. And I think I have another slide here showing those two things side by side. So if you look here on the top and the bottom on the left side, the top is just an image, a picture of the sky. And the bottom is the same picture, but then the light going through a prism. So each point that you see on the top becomes a trace on the bottom. And those traces, if we look at them really, if we really squint your eyes, you will see some of those discontinuities, and then you can actually measure the chemical composition. And the same happens here on the right-hand side. Here you have a star, and this trace here is just the same star, but then the light just going through a prism. And if you see those really tiny discontinuities, those translate to those lines in here that I can measure, and I can tell which element isn't there and by how much, right? So then we'll talk a little bit about now this thing about different types of photometry and different types of spectroscopy. So for example, so when we talk about photometry, you may think of pictures of the sky, just the one as you see on the right-hand side, but astronomers, they do things a little bit differently. Sometimes in order to get more information from the objects that you're trying to, well, characterize, what you do is you put filters in front of your camera, right? So you can think of, for example, I point to the galaxy and then I take a picture. Then I put a blue filter in front of the camera. And by blue filter, I mean that the blue light will be passing through the filter and everything else will be blocked. The red, the green, and the lights will be blocked. So you do that with a blue filter, with a green filter, with a red filter, and so on and so forth. And this is what you see, for example, on the left-hand side. All of the names that you see on the top right, so these are just names of different filters that go from blue to red. And notice how the image actually changes as you go through the filters. This is the same object, right? So that is telling us that the object has, for example, objects within that galaxy with different temperatures. Because in some of the blue filters, you see, for example, that there's things in here that shine a little bit brighter depending on the filters, and other things that they just almost disappear depending on the filter that you're looking at. And then what we do on the right-hand side, we just combine all of them to have the pretty picture so we can have, on the publications and press releases. But then what we do in order to characterize temperature and chemistry of some objects is to look at all of those filters individually. Yeah. Leilani, you have something?
Yes, we have another comment. Great presentation, Vinny, so far, of course. And we have our first question from the YouTube chat, which is, does the location on Earth impact the intensity or reading of the light for when you do these calculations?
Yes and no. Well, yes, meaning if you are, for example, if you go to Mauna Kea in Hawaii, you're really high up, right? Really high altitude, the sky is perfect. So then you have a clearer view. So then you can have better measurements. For if you go for Chile, is the same thing. But if I go, for example, to a big city like Sao Paulo, where I was born, you can barely see the sky. So in that sense, yes, they would affect what I'm seeing. But for astronomers, in order to make sure that we are not biased or are not biasing our observations because of the location, we have ways of calibrating the flux, right? So we can observe well-known stars for which we really know the flux, and we can know how the flux is attenuated based on altitude or based on location on Earth. So that's a very good question, but astronomers have ways of calibrating observations. So in principle, for those professional astronomers doing science with those images, it shouldn't matter where you get your observations, right? They should all be cross-calibrated, and you should always get the same numbers, if that makes sense, right? Yeah. Okay, so one way of finding interesting objects is just like this, right? You see the different filters here, and it's amazing that the more you look at an image like that, the more interesting things you start to see. You can see, for example, the really bright dot here on the bottom left. So these are actually two stars, I think. And you see, as we go towards those redder filters, it shines really bright, and all of a sudden it almost disappears. And that means that that star has more flux towards the red. So that translates into some temperature changes. So that's, let me just make sure I'm on par with my slides. Yeah. So this is one of the techniques I use to find this very interesting star that I'm talking about. And that star is actually here on the right-hand side. That's the star really here, right in the middle of the picture. So that's the one. So if you look closely, when the filters are just one after the other, you see that the brightness of the star, it changes a little bit, right? There's more than one effect playing here. But in principle, you can pick one star on the field and keep looking at it, and some of them actually disappear depending on the filter that you're looking at. So if you can get information from two different filters, for example, I look at one filter where the star is there, really bright, and another one that it's really faint, and I subtract those two filters, that can give me actually physical information about the star. And here on the left-hand side, I'm just showing what we call the filter curves for this survey. It's called Southern Photometric Local Universe Survey. It's a survey developed by folks at the University of Sao Paulo in Brazil. So the telescope observing for this survey is actually housed by our friends at Cerro Tololo Inter-American Observatory. And that survey observes with those 12 different filters that you see here. And the colors are actually pretty close to the light that those filters are letting through, right? You see here U filter and those, some sort of a violet and then blue, green, yellowish, and red. So what that means is that, for example, this filter here, 515, it blocks all of the light from the object and it just lets it through yellow light. And it does that for this entire field, for example, here, right? And then by comparing those different colors, so take a look at those names here. If we subtract those colors, we can actually have an idea about physical parameters of those stars. And this is what I have here. So I won't go into much detail on this, but I just wanted you to have a look at those two names here. See, that's 410, 861. We don't need to know exactly what they mean, but I'll just go back to the other slide. So these are two filters that are listed here. So they are actually probing the light from different parts of the electromagnetic spectrum. And once we subtract those two, we have what we call a color index, and we can correlate that with the surface temperature of the star. So it's a very clear correlation here. So if you give me two pictures of the sky in those two different filters, I subtract those two, and I actually have temperatures for many, many stars, which is, well, amazing, right? Jamika?
Yes, Vinny, I'm loving your explanation of how the filters work here. I was curious, could to make an analogy to maybe something that regular citizen scientists, amateur astronomers would have had some experience with, like neutral density filters that only let through, light, a certain light, so that you can see the sun in all of its glory. Would that be an analogous comparison to the filters that you're using here in their function?
Oh, absolutely. Yeah. Yeah. Absolutely. Yeah. Yeah. So it's the same thing. So these are just, blocking filters, or you have a band pass. So what happens is you have to know which light or which color of light you want to come through, right? And those filters here, they were specifically designed to probe very specific physical parameters, like the ones I'm showing here, right? But that's the exact same thing, right? If you have a camera and you have those different density filters and blocking filters, that's the exact same thing. Yeah. So as you can see here, just by subtracting two images, you can actually have an idea of effective temperature for the stellar sources. And this is really, really interesting, right? And if you look on the right-hand side, even though the math here is a little bit more complicated, and instead of a J, you have an F, but that's the exact same thing. What you're doing, you're combining the data coming from those images in a way that would give you, for example, an idea of the metallicity here. So, and in here, what I'm showing is just two colors. Think of these as just two colors, two subtractions of two images. And what it's telling us here, and this value here is what we call the metallicity, the amount of iron on the surface of a given star. So what this is giving us is just a map of how those metallicities behave as a function of those colors. And this is super powerful, again, because you're just looking at images. And if you work cleverly enough with all of those images, in principle, you can say, well, if I really like stars with this particular metallicity, I will look in here. I'm not looking over here or over here or over here, right? I just look at the right place. So all of those filters, what they're giving us is just an ability of pre-select interesting targets so we can do the spectroscopic follow-up, which I'll talk about in a moment, right? So what's nice about these techniques when we're talking about photometry is that as an astrophysicist, what you would like is when you see a picture like this, I would actually like to know or have a spectrum of each and every one of those points on this entire image, right? That would be a dream come true. However, this is not possible. It's not feasible in terms of time, in terms of investment. So there's a lot of roadblocks. So what I have to do is I have to look at an image like this and say, which one would be the most interesting star on this entire image that I would actually have to ask for time to go on a big telescope and observe. So that's where things like the narrowband filters come in, because if I do those color differences, just as I showed here, I can pick stars, for example, of a given temperature and of a given metallicity and say, hey, I can select those on this big image and find what we call the needle in the haystack. Because it's just, there's so many stars in the sky that we cannot possibly have really detailed studies of all of them. Maybe one day, but now this is completely impossible. So what we did for this particular survey, we used 3 telescopes, 3 different projects in order to identify just one very, very interesting star, right? And those 3 telescopes were these ones. The one on the left, you see it's called the S+ project, as I mentioned. So the S+ telescope observed about 20 million objects using those 12 filters that I just showed you. So out of those 12 million objects, what I did all of those color combinations, I did all of those graphs, and I selected 200 objects. And then those 200 objects, I submitted a proposal to the Gemini telescope to do spectroscopy of those, what we call medium resolution spectroscopy, that gives us some amount of information of the chemistry. And using what we call the Spur weather program, that it's a very nice feature of the Gemini telescope that gives you time to observe for free when the weather is not very good, right? So and we can talk about this later as well. Leinani, you have something?
Yes, we have a question for you from YouTube. It's, what classification of stars are usually metal poor? O, B, A, F, G, K, or M, or does it vary?
Well, the ones I work a lot with F, G, and K stars, and these are what we call spectral types. I think this is to do chemistry work. I think this is one of the better temperature regimes to actually have those clear atomic species. But you can have stars that are a little bit hotter than that in terms of temperature, close to 8 to 10,000 Kelvin, that would also be low metallicity. And even if you go towards the cooler types, you can also have that as well for M dwarfs, M giants as well. Yeah, so it's a wide range. However, for this specific study, we do narrow it down to a smaller range of temperatures just because it's easier for us to do the spectroscopy and the chemical abundances, right? Okay, so 200, so from 20 million to 200, and then those 200s were observed at Gemini South. And then I looked at the 200 objects, I looked at their spectra, right? And then I selected one, which I thought was the most interesting one. And then I had a friend who had time on this Magellan Clay telescope, which is also in Chile. It's just on the next mountain to Gemini South. And then he obtained the high resolution spectroscopy for this particular star. And that's the star that we are going to talk about now. It's just showing this very interesting discovery. And well, this next slide here, it has a lot of information, right? And the name of the star is on the top, right? As you can tell, astronomers are not allowed to name stars because otherwise it would be a real mess. And sometimes when they allow astronomers to name things, you wouldn't, you know, I cannot even tell the names that astronomers come up with, so I won't, right? But yeah, so it's a catalog name. So it's S plus J2104 and so on and so forth, right? So the pet name is S plus 2104 minus 0049. So that star, it was first identified from its colors. So you can see here on the left-hand side, the colors on the 12 different filters. And I just put some color here, just so you have an idea of which filters are those, right? And you see that star, it gets brighter from the redder filters here. You see it's a little bit brighter here than it is in here and in here. And that's telling you something about its temperature and its chemical composition. So if I look at the photometry for this star, what I have here from S plus is just 12 pieces of information, right? So for each and every one of those pictures, I have a number which gives me the total flux of that star through that particular filter. So on the top panel here, I have, well, the 12 points of information, and this is all I have from photometry. So 12 points. And this image here, it took about, well, 10 seconds per filter to get that image. Leilani?
Okay, you've got 2 questions for you in the chat.
Mm-hmm. Sure.
The first one is, actually 3 questions.
Okay.
Great job, everyone. Keep them coming. The first one is, are the companies that offer payment to have a star named after someone legitimate?
I wouldn't spend my money on that. No, I think there's, you know, no. Again, I could say that this star here is called whatever I wanted to call, but for the International Astronomical Union, right, you need to have some sort of a catalog name because people need to be able to find that star. And the reason we call this star S plus something something is because, well, S plus is the name of the survey. And all of those numbers you see here, it gives you the exact position of that star in the sky, right? So, well, you can pay to name a star, but that means absolutely nothing. Sorry. Yeah.
All right, thank you, Vinny. Our next question is, how often do you go to the telescopes in order to get all of these results?
Well, not often enough. I think it's becoming rarer and rarer now. Well, with the pandemic now, it was completely shut down. But depending on the type of science you do, when I was working at Gemini, for example, I would go maybe five days per month, or something like 5 nights per month, or 5 nights per shift, something like that. Nowadays, with the internet and fast connections, most of the observations we can do it from home, right? So the ones at Gemini, for example, you can just submit the observations to the observatory, and they will do the observations for you when it's more convenient for them in terms of time and scheduling, right? So not as often, but I think it's a really great experience to be there and do the science by yourself or on your own. But doing this from home, I think it saves a lot of time. It saves resources. And yeah, so last time I did that was over Christmas. So I actually had 11 nights towards the end of the year. So I spent it wasn't a big hit in my family, but I spent Christmas observing. And again, you just sit in front of the computer for the entire night, and then you just emulate what's happening at the telescope here, well, in your apartment. It's not as fun, but yeah.
Thank you for that. All right. And our last question for now is, how many observations happen to collect all of this data that you and your team have used for this project?
Let's see. So the S+ survey, those 20 million objects that I mentioned, I think this survey is happening now for a few years now. So I think it took them a few years to collect the data and process the data, because the processing is super hard to get all the accurate information, right? So then for the Gemini data, those 200 stars that I mentioned, maybe it took me about a year combined, right? It's some sort of different telescopes. And the final one that gave us this high resolution spectra that I'll talk about in a moment, that was just one night. It's just 1 hour of a big telescope that gave us the actual data. Yeah. Is there another question?
There is, yes.
Mm-hmm.
Lots
Sure.
of questions in the chat, which is great.
Mm-hmm.
Okay, our next question is, what role does the International Astronomical Union play in astronomy?
Well, I think it's some sort of a body that makes sure that we have all the proper governance in terms of policies, in terms of regulations, and in terms of identifying members of the community of all sorts of different places, and having, for example, outreach opportunities just like we have here. So it's a governing body that maybe collects and all the astronomers, well, on the entire planet, right? We have the American Astronomical Society, we have the Brazilian Astronomical Society, and all of those are separate within their own countries. But the International Astronomical Union, what it does is just collects everything, right? And make sure that we have proper policies and proper procedures for, research and everything we do in terms of also outreach and everything else. Okay, good. No, these are very good questions. All right, so back here to our discovery, our J2104. So as I told you here on the top right panel, for S+, we only have 12 points, right? 12 pieces of information. And those come, well, relatively free because those images were there already. So in order to get those 12 points, you only need 10 seconds of exposure for each filter. And once you go through a telescope such as Gemini, for example, and you want to have a medium resolution spectrum, and here, what I'm doing here is just zooming in on this particular region, and then you blow up this region, and then you have what we call the Gemini spectrum. And each and every one of those, this line here is made up of about, 1,400 points, so 1,400 points. So from 12 points, we go to, 1,400, which is a lot more information. And then instead of 10 seconds, then it takes 5 minutes, right? And you see it's more expensive in terms of time. And then once we declare from the middle panel that the star is really interesting, we go to the higher resolution spectroscopy. And that becomes super expensive in terms of time. And you see here that I'm just zooming in on this tiny region here on the red box. So only this region here, if you go to this high resolution spectroscopy, all of a sudden you have 22,000 pieces of information. So you go from 12 to 22,000. And then 22,000, it's a lot more information. So you can get a lot, you can get better information, and you can have your accurate chemical abundances. And to get that type of information, then you have to sit in one star for an entire hour in just one star. So then it's a big time investment. So we would never be able to do this for all of the stars, in the sky, right? So that's how that star was discovered. And then you may ask yourself, so why is this star so important, and what's the big fuss about it? And Jamika, you.
Oh yeah, no, I was going to ask that, because you had all these potential star candidates. Why this star? Why is this star so important?
Yeah, so it's important because once we got this high resolution spectrum, we calculated the chemical abundances that we could, and we found that this star is really interesting in terms of its metallicity, so in terms of its iron abundance, and in terms also of its carbon abundance. So if you look at this plot, I won't give you much detail, but that's just some sort of to have an idea. So these are all of these stars that we know to have low metallicity and be observed in high resolution. So there's not a lot of them. And if you look at the ones with those metallicities here, the Fe over H below -4, we only know of 35 of those. And when you look at the carbon abundances here on the y-axis, most of those, they have high carbon abundances. And as I told you on the second slide, carbon is considered a metal. So even though they are ultra metal poor in terms of the iron, they do have lots and lots of carbon. And that fits a little bit the model that we believe it's correct for the first stars. But this particular one, when we found it and we determined the carbon abundance, we realized that it's super, super low. So it's here, right? So based on all the other stars, that star should actually be up here, someplace in here, if it was just following the average. But in fact, it's actually down here, meaning that not only the star has just a little bit of iron, but it also has, well, just a little bit of carbon. And that fact in itself, it challenges some of the current models for the chemical evolution of the entire universe. And what's interesting about this, and well, it may not seem interesting at first, is that, well, we observe this star and we know that it doesn't have a lot of carbon. So that means that the universe knows how to form such stars, right? Because the star exists, it means that the universe could form it. So if the universe could form such a star, now we have to find an explanation for it. We were not expecting to find this red dot over here, right? There was nothing here before. So if we did find one star in here, now the challenge becomes, well, can we find more of those? And if we can we actually explain why the star is here and not, well, up here with the other ones? So that's now the next part of a study like this. And something else that we can do, and I'll just show you a plot very briefly, is to compare all of the measured abundances for a star like this one with models, with predictions from supernova explosions. So what I'm showing here, and I know it's also a very busy graph, and I won't go into much detail, is the abundances measured for this particular star. So all the circles you see, they are the abundances of the elements labeled here on the bottom. So carbon, sodium, magnesium, aluminum, silicon, all the way to zinc. So we could measure all of those elements in the star. And each and every one of those lines is actually a model predicting what would happen when a supernova of a given mass would explode. What would be the chemical makeup of the explosion? So if we compare the chemical makeup of the explosion with the elements we see on the star that was formed right after, I can tell some characteristics of the parent population. And these are constraints that people really want to know, people doing Big Bang nucleosynthesis or first star nucleosynthesis. So our observations, they drive some of the theoretical work, because now that we have the observations, people need to explain why those observations are here in the first place, right? And that's, well, the interesting part of the discovery, right? So the star was not supposed to be there, and as you can see here, it was really unexpected, and we were able to just, well, publish a very interesting result about this particular star. And what I do have now here towards the end is I'm showing, so this is just, well, the top part of the paper that was just published last week. And I think at some point I was chatting with Jamika, and she wanted me to talk a little bit about, well, how do you publish those research results, right? So how do you go from observations to an actual final result? And in our particular case, the final result is something like this, is a publication, right? It's an article. Well, we call it paper, but nobody prints those anymore. And well, they're not printed at all. But so this is the final product, right? So we do the research, and then we report the research in this case, this is the Astrophysical Journal Letters, and it's peer reviewed. So that means that we write about the discovery, and we just submit this paper to the journal, and then the journal identifies people who would be willing to judge the work, and then they would review the paper anonymously. They would give us feedback, and if the paper is acceptable, then the journal would publish it, right? And just so you have an idea, the entire process from going from these S+ images, the 12 images, and I'll go back here real quick. So the process of going from the left-hand side all the way to the bottom right, and then to this plot here, and then to this one here towards the paper, in this particular case, it took about 1 year of work. And not only from me, right? I think a lot of people helped me, collaborated with me, and these are just the 9 authors of the paper that you see here, named here. But there's so many other people who, well, helped all of those facilities to become available, and the data to become available to the public as well in the form of those online free catalogs. So I think that's actually my last slide, and I'm be happy to take any other questions. Is there anything I needed to cover that I forgot, Jamika?
No, I think that that covers everything so far that we discussed in preparing for your presentation. But I do have a few more targeted questions, if that's okay.
Absolutely, yeah.
All right. And just as a heads up to those in our YouTube audience, we have about 9 minutes left. So any more comments and questions for today's guest, Vinicius Placco, please put those in the YouTube chat at any time, and Leilani will bring those over to us so he can address them. Okay, so in your paper, you talked about population 3 stars. So there are population 1, population 2, population 3. Can you give us a brief explanation about what those different population of stars are?
Yes, so in very broad terms, population 1, I think these are, well, mostly young stars. So stars that are just being formed now, blue stars, really high temperatures, and you can tell that these are just population 1, really young. Population 2, some people would call the sun a population 2 star in terms of its temperature and in terms of its age, right? The sun is 4.5 billion years. So, well, it's kind of old, right? It's not as old as the universe, but it's a little bit old. But depending, the classifications are not clear cut. And so the population 3, for example, that's a little bit more well-defined because we think that population 3 are just the first stars to be born in the universe, period. We never observed any of those, right? Chances are that we could, by looking for those ultra metal poor stars, maybe we'll stumble upon one of those, right? And so these would be the population 3. And for example, this star here, we call this a population 2 because we believe that that one was formed from the population 3, right? Or a second generation star. And again, this, the classification population 1 and 2 is it's really debatable, right? And we avoid that to a certain degree. But I usually think of those as, well, young blue stars, red old stars, and first stars.
Okay, good. I appreciate that explanation. Okay. And so with those different population of stars, as you said here, you're relating what you were looking at to population 2 stars. All right. Thank you for clearing that up. And just a quick question, though, about the process of getting the paper published. As you said, you have all these collaborators, all the people here at the top that we can see all their names. So all of that has to be coordinated. And so when you send in this information all together at once, then they're listed here with their affiliations and everything. And you said it took about a year for this particular paper to come out. Now, is that because you had such a large collaboration to work with, or is that more of the average amount of time it takes from getting research done and the data published in a paper?
Mm-hmm. Well, it depends a lot on the size of the collaboration, on the type of science. And in this particular case, since it was a discovery of an interesting object, we published this as a letter. So this is a shorter paper, so it has, I think, 8 pages, and papers can have 20, 30 pages, right? So that, it depends a little bit on the type of work that you're doing. So in this particular case, writing the paper took me maybe about 3 to 4 months of solid writing and reviewing and putting things here and there and making the graphs and the images. And then the rest of the time was doing the actual analysis. And these are not self-excluded, right? You can write a little bit while you're doing the analysis, but you want to have your analysis at least advanced enough that you know what you're going to write about, and the method section and all the introduction, and yeah.
Okay. Ah, wow. Sounds exciting. Leilani, you're back with some hopefully comments from our YouTube audience with about 5 minutes left.
Yes, we have two comments. The first is from Mauricio, says, great presentation. It makes physics look easy, which it definitely isn't. And our next comment is, congratulations on your well-deserved accomplishments. And then we also have a question. When stars explode, does any of the residue reach land? And if so, how long would the journey take?
Oh, yeah, no, I don't think it would. Well, just because stars are really far apart from each other, right? And the reason the Earth is still here is because the sun is a very boring star, right? It doesn't do much, right? The sun will never be a supernova. And if you did have a supernova happening close to a planet, then, well, you would be gone in no time, right? Because then the explosion would just, wash everything away, right? But stars, they are surprisingly far apart. So we think of star collisions and things like that, but stars, they are super far from each other. I think maybe I'm misquoting, but I think that if you take the closest star to the sun, and I think it would be, what was that? So if the sun was a basketball in Chicago, the next closest star would be a golf ball somewhere in Germany. So this is how small and how far two stars are. And this is the closest star to us. I may be misquoting, but I have this written somewhere. So stars in general, they're collisionless particles, as we like to say. Gas is different, but stars, no. And if the sun would explode as a supernova, then you would know pretty fast. Yeah.
Thank you for that. We have another question. It says, do you expect to discover more ultra metal poor stars using the S+ data? If so, how many?
Yes, we do expect. Based on the current statistics we have, I think we hope to find at least one ultra metal poor stars per 100 square degrees of the night sky, right? So a given patch of the night sky, we should find one. So if we have 10,000 square degrees, then there's a number of stars you can still find. Yeah, so they are definitely there. They are rare, but we didn't find all of them yet. So yes, absolutely. Yeah. The search continues. Yeah.
Well, thank you so much, everyone in our YouTube audience, for all of your questions and comments today, all of your support for our show, and for today's guest, Vinicius Placco. So, Vinny, as we wrap up here, may I do a screen share here? We're going to talk about our upcoming Live from NOIRLab next week. So before we move on to next week's show, we should have the recording of today's show posted by this Friday, and all of the links and information that Vinny presented today that has links, we will have in the video description, as well as the Cosmoview videos and news that we talked about at the very beginning. So we'd like to say thank you so much, Vinny, for joining us. And since the last question asked you if you expected to find more ultra metal poor stars in the S+ data, maybe we can have you back in the future with an update.
Oh, absolutely. Yeah. Well, we hope to find more of those. And well, thanks everybody for joining in. Appreciate the support from everybody. You know who you are, so appreciate it. Thank you.
Thank you. All right. So next week, let me pull up my slide here. So next week, we will have on Wednesday, Live from NOIRLab is actually going to be our in vivo Desde NOIRLab. This is with our host, Manuel Paredes, I believe. And on this episode, their guests are going to discuss this new lighting ordinance. So they're going to be talking about this update to the standards of lighting in Chile and the protection of the night sky for all Chileans. So that's going to be next Wednesday right here on the NOIRLab YouTube channel in Espanol. Okay, so I'd like to say thank you so much, mahalo nui loa, Vinny, for joining us. And again, also to my colleague, Leinani Losi, for so expertly and awesomely moderating the YouTube audience. Thank you so much, Leinani. Thank you so much, everyone, for joining us. And we hope to see you next week on